Hello and welcome back to Physics VR. This is Amir Khan, and today we will discuss about acceleration due to gravity and the effect of height and depth on acceleration due to gravity. So without wasting any time, let us jump forward. Now, before starting acceleration due to gravity, we must know about free fall. So what is free fall? A body is said to be in free fall if it is falling down only under the effect of gravity. So a body which falls only under the effect of gravity is experiencing a free fall. Now let us consider anything. Let us consider me dropping this. You can easily see that if I am dropping something, its velocity is increasing down. So, it is experiencing an acceleration. So, the acceleration experienced by a body in free fall is known as acceleration due to gravity, which is denoted by small g, and its value near the surface of Earth is 9.8 meter per second square. We can also find the formula for acceleration due to gravity by considering the weight of the body acting downward to be the force of the body and comparing it with the gravitational force. So we know that the gravitational force F is given by capital G, mass of Earth, mass of body upon radius of Earth whole square, and the weight of the body is given by F equals to mass of body into the acceleration due to gravity. Now if we compare both of them to be equal, we will have mg equals g m upon r square. M cancels out with m. We are left with g equals g m by r square. If we place capital G to be 6.67 10 to power minus 11, mass of Earth to be 6 into 10 to power 24, and radius of Earth to be 6.4 10 to power 6, we will get G to be approximately equal to 9.8 meter per second square, which is the value of G at the surface of Earth. So now we will discuss about effect of height on acceleration due to gravity. Let us consider the Earth to be a uniform sphere of radius r, and let us take a point P outside Earth at distance h from the surface of Earth. So the total distance of the point P from the center of Earth is r plus h. We can find out the acceleration due to gravity at the surface of Earth to be gm upon r square, which is to be equation number 1, and the acceleration due to gravity at the height h from the surface is to be gm upon r plus h whole square. Equation number 2. If we divide equation number 2 by equation number 1, we will have gh by g to be equal to gm upon r plus h whole square into r square upon gm. Gm cancels out. We will have gh upon g to be equal to r square upon r plus h whole square. If we take out common of r from here, we will have r square here, 1 plus h by r square. R square and r square cancels out, and we will have gh equals to g into g upon 1 plus h by r whole square. If we consider h to be much smaller, we can also have gh to be g by 1 plus h by r whole square or g into 1 plus h by r to power minus 2. Now, if we are considering a binomial expansion, taking h to be much smaller than r, we will have gh equals g into 1 minus 2h by r. So now we will discuss about the effect of depth on the acceleration due to gravity. For this, let us consider the Earth to be uniform sphere of mass capital M and radius capital R, and we have dug deep inside the Earth at depth d, and now the radius left is r minus d. Since if you have studied shell theorem, you might be knowing that now we will only consider the mass of the body from the point left. So, from the previous time, the acceleration due to gravity at the surface will be given by gm by r square. And if we go for mass, which is volume into density, then we will have g by r square into 4 by 3 by r cube rho, which gives out 4 by 3 by g r rho. Equation number 1. And now the mass of the body, mass of Earth from the point P inward is given by 4 by 3 pi r minus d's cube, because now the radius is r minus d, into rho, which gives 4 by 3, okay, which is this. Now the acceleration due to gravity at depth d will be g m dash upon r minus d's whole square, which becomes g upon r minus d's whole square into 4 by 3 pi r minus d's cube into rho. This square and the cube cancels out, and we are left with gd equals 4 by 3 pi g r minus d rho. Equation number 2. Again dividing equation number 2 by equation number 1, we are left with gd by g equals 4 by 3 pi g r minus d rho into 3 by 4 pi g r rho. Everything cancels out except r minus d and r. So now we are left with gd equals g into r minus d upon r, or gd equals g into 1 minus d by r. Next up, we will discuss effect of latitude on acceleration due to gravity. Now, let us consider the Earth to be a uniform sphere of mass capital M. This is the equatorial line and this is the axial line passing through the Earth. Now let us consider a point P at an angle del lambda from the equatorial axis, which is latitude. Now this body is moving, so it will now have a circular radius of small r. This is the radius capital R. Okay. The centrifugal force acting on the body will be m r omega square, and if I draw it correctly, I will have lambda here also, p to be here, and this will be m r omega square cos lambda, and this will be m r omega square sin lambda. The weight of the body will be acting downward towards center like this, mg. So this is a total diagram. If I have to find the relation between small r and capital R, I can use the relation. If this is lambda, this is lambda, this is lambda. I can use the relation of triangle. This is a right angle triangle. And from this right angle triangle, we can have that it is a base and it is the hypotenuse. So base upon hypotenuse becomes cos theta. So we will have cos theta equals r upon capital R, or small r equals to capital R cos, not theta, sorry, lambda, cos lambda. Now take to be question number 1. Now if we see it from this figure very clearly, from this three-block diagram, the weight of the body is acting downward and the centrifugal force has some component acting upward also. These two forces are in opposite direction, and the apparent weight of the body will be given by m into g lambda to be equal to mg minus mr omega square cos lambda. If we take out common, m into g lambda equals m into g minus r omega square cos lambda. M cancels out, we will have g lambda equals g minus r omega square cos lambda. Using equation number 1, we will have g lambda equals g minus r omega square cos square lambda, which is the required equation for the effect of latitude. From this formula, it is really clear that if we are at the equator, cos lambda equals to cos 0 degree, which is equal to 1. So g lambda equals to g minus r omega square, and if we are at pole, we will have cos lambda to be cos 90 degree, which is 0, or g lambda will be equal to g. So clearly at the pole, acceleration due to gravity is greater than the acceleration due to gravity at equator. So we will have g lambda at equator and this to be g lambda at pole. So we can say that g lambda at pole is greater than g lambda at equator. So this is all for today's video. Feel free to suggest in the comments box below what video should we make for the next time. If you have liked this video, press the thumb button, and if you have loved our videos, do subscribe to our channel and share our channel to others